Hello, this is an educational video about diagnostic methods and ultrasound by Adam, Matthew and Rachel. First we'll start off with radionuclides and radiopharmaceuticals. The best type of emission is gamma, as it will not be fully absorbed by the body and is less ionizing compared to alpha and beta. Non-invasive techniques are required as they reduce infection risk, recovery time and cost. Here are the reasons for wanting a short half-life. Radiation will be given out quickly, but enough to form an image on a gamma camera. Any remaining radiopharmaceuticals will soon decay, decreasing a patient's exposure to hazardous radiation levels. Radiopharmaceuticals are radionuclides chemically combined with other elements taken in by the tissue. The same radionuclide might be used to look at different parts of the body. Here are some examples of radioisotopes and their uses. We'll only be talking about titanium-99m, as that normally has questions asked about it. So, it's used for bone growth, blood circulation in the lungs, brain and liver, and the function of the thyroid and kidney. This is the gamma camera. Gamma photons pass through the collimator, a honeycomb of cylindrical tubes in a lead plate, cutting out any photons not travelling along the axis of the scintillator. Beam of gamma photons strike the scintillator crystal, where each photon produces several visible light photons. Light is detected by the photomultiplier tubes that produce one electric pulse per light photon. One light photon releases an electron from the photocathode via photoelectric effect, where the electron is accelerated to a dynode producing 2 or 3 secondary electrons. This process is repeated, increasing electrical impulses which are processed electronically by a computer. The position of the emission of the gamma photon can be located from the output of the photomultiplier tubes. This is positron emission tomography, also known as PET. The radiopharmaceutical used is fluorine-18 and glucose. The emissive particle is a positron, which is beta plus. When its positron meets an electron, they annihilate. Their masses are released as energy in the form of 2 gamma photons travelling 180 degrees to each other. Line of annihilation computed by gamma ray detectors, recording of the times of the 2 gamma rays travelling in opposite directions from the patient. Using the time delays and knowing gamma travels at the speed of light, the position of the emission can be calculated. This is used to show that cancerous tissue, brain activity, or normal bodily functions. Magnetic spin. Neutrons and protons have a property called spin, linked to magnetism that can be in one of 2 directions. If a nucleus has an even nuclear number, half will spin each way and have no net spin. Nuclei only have net spin if they have an odd nuclear number, for example, carbon-13, phosphorus and hydrogen. Nuclei with a net spin have a magnetic north-south axis, which corresponds with their spin axis. In diagram A, hydrogen is not normally magnetic, as all magnetic axes point in random directions. In diagram B, in a strong magnetic field, hydrogen nuclei will line up with a magnetic field. Unlike normal magnets, there's only a small proportion to line up in the same direction as the field. Many will point the wrong way. In C, in the left corner there, crucially, magnetic axes do not quite line up with a magnetic field. The axes rotate about the field. This is precession. Precession and imaging. Lumar frequency is the frequency of precession. If you apply pulses of radio frequency to EM radiation at the lumar frequency, energy is absorbed due to resonance. Some of the protons that are aligned the right way are flipped to be aligned the wrong way with the magnetic field. These will flip back or relax, emitting an RF signal as it transfers from high energy to low energy. This is related to the number of nuclei and decreases over time with characteristic relaxation time. These principles are used in magnetic resonance imaging. In the imaging, relaxation times for hydrogen vary depending on the proton's environment. In water, relaxation times are longer, and in fat are shorter. This can be used to distinguish between different tissues. The positrons can be identified using magnetic gradients, which give slightly different Lumar frequencies for every point in the body. MRI, the equipment. On the left, we have a table with features and functions. If you want, you may now pause the video to read through these. On the right, we have the advantages and disadvantages. For the positives, we have there's no use of ionizing radiation, and there's no moving mechanisms, only changing fields. The patient feels nothing, and there is a better soft tissue contrast than CAT scans. For the negatives, we have any metallic objects in the patient will heat via electromagnetic induction. People with heart pacemakers can be affected. The room must be shielded from external fields and contain no steel objects that could be attracted to the magnets. It does not show bones as clearly as CAT scans, and it's also very expensive. Ultrasound and production. Ultrasound is sound waves above 20,000 Hz. Medical use frequencies in megahertz range. High frequencies give high resolution. Too high and tissue heated, so waves absorb more. Production. Piezoelectric transducer used, both transmitter and receiver of ultrasound. An AC supply is applied to the crystal, causing it to contract and relax. This generates ultrasound waves and is known as the piezoelectric effect. When pulses reach the surface, it can be reflected or refracted to the next boundary. Detection and A/B scans. When pulses reach surface, it can be reflected or refracted to the next boundary. Refraction reflected depends on acoustic impedance of materials. If the reflected ultrasound waves strike crystal, varying stress results in voltage, which varies with frequency of ultrasound. This is used in order to determine the material, i.e. tissue and bone, and the thickness at which they occur in the body. A scans. A pulse is sent into the body, and reflected echoes displayed on oscilloscope as a voltage time graph, only in one direction. A B scan. It's many A scans, a detailed image of cross-section through patient built up. Each reflected pulse analysed to determine depth of reflecting surface. 2D image built up on screen by positioning dots to represent position of reflecting surfaces. More dots, more ultrasound reflected. It's from many directions and angles. Acoustic impedances. With ultrasound, we are interested in the fraction of the indecent intensity of ultrasound that is reflected at the boundaries. This depends on the acoustic impedance said of each material. This is defined as density times speed of sound. The ratio of reflected intensity is equal to the acoustic impedance of one minus the other, divided by the other one plus the other, all squared. Problems that occur. An issue that occurs is that the air between the emitter has a small acoustic impedance, so a coupling medium like oil or gel that have a large one are used so more ultrasound can get into the body. The Doppler effect. The Doppler effect can be used in ultrasound in order to determine the rate of blood flow in an artery. This is how it works. A sound source is sent towards the artery. If the sound source is moving away, it's heard as a low frequency. The effect is doubled if wavelength is sent out to reflected back on the moving target. It monitors action of heart as it beats. Thank you for watching. Please make sure to like and subscribe.